Acha. So we have completed the revision of first 5 chapters from electricity magnetism, and today we are going to revise the 6th chapter, that is electromagnetic induction. Alright, now you may recall from our previous chapters that, well, in particular, the expression for the Lorentz force. Okay, what does the Lorentz force tell us? The Lorentz force tells us that if we have moving charges, okay, if we have moving charges, only then they will experience the magnetic component of the Lorentz force, isn't it? So moving charges can change their direction, okay, when they are placed in magnetic field. When they are placed in magnetic field. Now we ask the converse question. If we change the magnetic field, okay, so by some means, if we change the magnetic field, can it cause the charges, the stationary charges to move? And the answer is yes. That is what we call electromagnetic induction. Let me repeat what I said. When you have a charge moving in a specific direction with velocity v bar, and if it enters a region of magnetic field, then it experiences a force and therefore it accelerates. Okay, that is what we calculate in using Lorentz force, which is F bar equals, I'm not writing the electric field component now, so it is q v bar cross v. So if magnetic field if moving charges can experience magnetic field and undergo or change their direction, can change in the magnetic field cause the charges to move? And the answer is yes. That is what we call electromagnetic induction. That is converse of this. Okay, so in a nutshell, if I want to define electromagnetic induction, what would I say? Time varying magnetic fields. We know that it is not actually magnetic field, but it is actually magnetic flux. Time varying magnetic flux induces EMF, and therefore if we complete the circuit, then electric current. Now, to demonstrate this electromagnetic induction phenomenon, two people were involved. The first one was Michael Faraday in the United Kingdom, and the second one was Joseph Henry in America. So we will not again discuss in detail what the experiments were all about, but this is the outline. In the first experiment, there was a coil C1, which was, and there was a galvanometer connected to it in case a current flows through it. But right now there is no battery. And what both of them observed is, when a bar magnet is moved, okay, basically whenever there exists a relative motion between the bar magnet and the coil, then there is a deflection. That was observation number one. And then there were some secondary observations, like if you increase the speed, then the deflection is more. If the north pole is approaching, deflection is in one side, the galvanometer. If the north pole is receding, then the deflection is in the other side, and so on. And yeah, okay. Number two, if this bar magnet is replaced by a coil, okay, which has a battery, by the way, which has a battery, so it has current. Now, instead of this magnet, if we move the coil in and out, again you see a deflection in the galvanometer, right? And these lines that are there in your textbook, okay, what are these lines? These lines are lines of magnetic field. So tangent to that will give us the direction of magnetic field, and the number of lines passing through any given area is an indicator of the magnetic flux. Okay, magnetic flux. Experiment number 3. In experiment number 3, we learn that the relative motion that exists between the coil and the magnetic field is not an absolute requirement. Even if the current in coil C2 changes, you can still see a current inducing in coil C1, and that is why this tapping key is there. Okay, this tapping key, when pressed, current builds up. Okay, when you press the tapping key here, the current builds up from 0 to Imax, and when you open the key, then the current drops from Imax to 0. Whenever the current is increasing or decreasing in C2, you can see a deflection in the galvanometer connected to coil C1. This is the summary of the experiments which were performed by Faraday and Henry. Is that clear? Okay. Now what we are going to study or revise next in this chapter is the quantitative aspects. Okay, quantitative aspects of these experiments, like does it have something to do with velocity? Does it have something to do with the length? Does it have something to do with area, magnetic field? Of course, magnetic field is there, and so on. Okay, so we will study, revise Faraday's law, then Lenz's law, energy conservation, then motional EMF, and at the end we will introduce ourselves to the concept of inductance, both self-inductance and mutual inductance, and at last we are going to revise generator. Alright. So it is very much essential to define magnetic flux. What are the requirements to define magnetic flux? We need magnetic field. We need a magnetic field B bar, and we need an area. Okay, we need an area which need not be closed. Okay, it can be open, so and it can also be flat or curved. Okay, we are not going to put any restriction on area. It can either be closed or open. It can also be a flat or a curved area. We are going to associate an area vector with it, as we usually do. Let us say that this area is okay. Let us say that this area is a flat area, so that the area vector can be considered to have just one direction here, and the magnitude of this area vector will be the magnitude of the area itself. Let us also assume that magnetic field is uniform. So suppose the magnetic field is here, this direction. Then the flux phi b, okay, magnetic flux phi b through area A is defined as B bar dot A bar. Okay, B bar dot A bar, scalar notation B A cos theta, where theta is the angle between magnetic field vector and the area vector. This is that. Later on, at the end of this chapter, when we study generators, there we actually differentiate theta with respect to t, and that is how sine theta or sine omega t term comes in the generator, and then frequency, alternating current, those terms come into play. Now, if magnetic field is not uniform, suppose if magnetic field is not uniform, or if area is not flat, okay, if area is not flat or both, then magnetic flux phi b is given by the integral, we call it a surface integral, over the area A of B bar. So it is B bar dot dA bar. Where else have we seen this integral? Can anybody tell me? Where else have we seen this integral? In which chapter or in which law?
Electric.
Yes, electric flux is there, but even the integral of magnetic flux, we have seen that in Gauss law of magnetism, if you remember.
Oh.
Yes, Gauss law in magnetism, what does it tell? It tells us that if we take the flux of magnetic field over a closed area A, that's why this symbol is there, then it is 0. Okay, the mathematical way of saying that magnetic monopoles are not found. Anyways, so magnetic flux is there, and this is the most important quantity in this chapter, because through magnetic flux and its relationship with current, we define inductance. If we differentiate magnetic flux, we get induced EMF. Okay, so magnetic flux is the fundamental quantity or the important quantity, the most important quantity in the entire chapter. हे लक्षात आलंय सगळ्यांच्या? Have you understood this? Can anybody tell me the SI unit of magnetic flux? Yeah, yes, exactly. Yeah, both are there. Weber or Tesla per meter square. Oh, Tesla meter square. SI unit is Weber. SI unit is Weber, or Tesla is Weber per meter squared. So Tesla. remember both these units. There is one more unit, and what could that unit be? It comes from the Faraday's law or Lenz's law. It is volt second. Volt second. Okay. EMF volts, time second. So Weber, Tesla meter squared, or volt second, or all are the SI units of magnetic flux. Next, Faraday's law of electromagnetic induction. This is the first quantitative statement regarding the observations that were made by both Faraday and Henry, according to textbook. What is the Faraday's law? The Faraday's law tells us that the magnitude of the induced EMF in the coil, the magnitude of the induced EMF in the coil is numerically equal to the magnitude of the rate of change of magnetic flux with respect to time. The magnitude of the induced EMF is equal to the absolute value of the derivative of the magnetic flux with respect to time. Now this gives us, this very definition gives us three ways to change magnetic flux. Okay, what are the three ways? We know that phi b depends on magnitude of p bar, it depends on magnitude of a bar, and it also depends on the angle theta between them. So if I change magnetic field keeping area and theta constant, there will still be a change in the magnetic flux. Correct? In these experiments that you see, that is what is happening. What is happening? Area is not changing, theta is also not changing, but what is changing is magnetic field's strength or magnitude. If you take the magnet closer to the coil, then the field will increase. That is one way to do that. If the area is, if area either increases or decreases, then still EMF is induced, and this is what happens in slide wire generator. This is what happens in slide wire generator. These are Faraday's experiments, and do you remember where do we change theta to generate EMF? Exactly, yes, generator. As in, well, there is a rotor which rotates, maybe due to turbine power, hydroelectricity, a stream of water may rotate the turbine, and connected to that turbine is our armature or the coil. Okay, the area of the armature does not change, but what changes is the angle which it makes with the magnetic field, and therefore theta changes with time, therefore magnetic flux changes with time. This is the Faraday's law of electromagnetic induction, the first mathematical or quantifying statement of the phenomenon of electromagnetic induction. Now let us go to Lenz's law and conservation of energy. Lenz's law tells us about the polarity of the EMF. Lenz's law tells us about the polarity of the induced EMF. Polarity of induced EMF. Mathematically, the induced EMF E is negative of the derivative of magnetic flux with respect to time. When everything is expressed in SI units, EMF volts, T seconds, and flux in Weber. So what does this negative sign signify? This negative sign signifies that the direction of the induced EMF, is such that it opposes the agency that induced it. What do I mean by that? Let's take a look at these figures. Consider a bar magnet approaching this coil with its north pole facing the coil. Correct? Now there are two possibilities. Just focus on figure A. There are two possibilities. Either the current will flow in the anti-clockwise direction when you look at it from here, or it can also flow in this direction. Correct? So which one of them is the right one? Experiments tell us that the magnetic moment of the induced current, because whenever a current flows through any closed loop, there will be magnetic moment, right? I into A squared. I into A. Area is constant, so current changes. If a current is non-zero, then it will have a non-zero magnetic moment. Now, I want you to take your right hand and I want you to bend your fingers, curl your fingers in such a way that they match with the blue arrows shown in the figure. What do you see? The thumb is seen to point towards the north pole of the approaching bar magnet. And this thumb also points out, indicates the direction of the north pole or the north polarity of the induced current in the circuit. Which means further this bar magnet goes closer to the coil, greater opposition it will face because of the greater induction of current, therefore greater magnetic moment. And that is signified by drawing this N here. This N is not made up of any wire. Okay, it is just to emphasize that when north pole approaches this coil, the direction of the current and therefore direction of the induced EMF is such that it always opposes the further journey of this bar magnet towards the loop. Now consider the second case. Suppose the bar magnet is receding. With its north pole facing the coil. Now you can see or check experimentally that the direction of the induced EMF and hence current will be opposite to what it was in the first case. Now why is that happening? North pole is receding. Just like the coil doesn't like the north pole approaching, it also does not like north pole receding. No change is acceptable. Okay, it will oppose the change. So it will call it back. It will call this north pole back. It will say, don't leave me. And as a result of that, the south polarity of this induced magnetic dipole moment will be facing the receding bar magnet. You can again check it. Take your right hand, curl the fingers of your right hand in such a way that they match the orientation of the blue arrows shown in the second figure. You will see that the thumb will now be pointing towards your right. Okay, that is away from the bar magnet. So if thumb is pointing towards north, this must be the south. So this will call it back, don't go. So either you move this bar magnet towards it or you move the bar magnet away from it. In either of the cases, you have to supply energy to that. And that is how the conservation of energy principle is obeyed. Otherwise, if I just push this bar magnet, it will continue to move unless there are any dissipative forces, and that will violate energy conservation because you are creating current out of nowhere. That is not going to happen. Okay, so the negative sign in the Lenz's law signifies that the conservation of energy principle is not disobeyed, it is always obeyed. Have you understood this? Yes? Clear? Okay. Okay. Yeah. Now let us talk about slide wire generator. The phenomenon is also called as motional electromotive force because in this case area is going to change and that change in the area is going to cause magnetic flux to change. Situation is very simple. As usual, our magnetic field is uniform and it is directed away from us towards the screen indicated by the blue crosses. That's V bar. We have a C-shaped frame, metallic frame kept in the plane of the screen or in the plane of the paper, and on this C-shaped plane, C-shaped frame, we have kept a piece of conductor which can slide in this direction. We can slide in this direction or the other direction. to and fro motion. Suppose we set this bar in motion with a uniform velocity v bar, so that it is moving away from this arm of the frame. I want you to tell me if the motion of this conductor is towards our right, what is happening to the area enclosed by the frame and this conductor? The area is increasing, correct? The area is increasing, but we don't care whether the area increases or decreases. Okay, no matter whether it increases or decreases, area is changing, therefore magnetic flux through it is changing, and therefore the EMF is induced there. Have you understood this argument that I have made? Okay, now let us apply the Faraday's law and the Lenz's law. E is equal to d phi b by dt. So what is induced EMF E now? D by dt of BA cos 0. BA cos 0, because both area and magnetic field are in the same direction. Cos 0 is 1, magnetic field is constant, B will come outside, cos 0 is 1, so it will be dA by dt. Okay, now the rate at which this area is increasing is actually equal to the rate at which this dimension is increasing. The rate at which this dimension is increasing. So if I call this as x, area will become A into L, area of rectangle, so it will be B, L being a constant, dx by dt, because area is Lx, and therefore the induced EMF will be BLB. Is that clear? The induced EMF in between the ends of this conductor, that is this end and this end, will be BLB. Have you understood this? Okay, now we can also arrive at the same expression of induced EMF between ends of a conductor of length L moving with velocity v in a magnetic field v using the Lorentz force. And to understand this, let us try to apply the left hand rule. Okay, we now need to take out our left hand. The middle finger should indicate the direction of the current. The index finger should point towards the direction of the magnetic field, and F will be the direction of the force. Okay, F will be the direction of the force. Now, well, we can use that formula, that F bar is equal to QV bar cross B bar, or F is equal to QVB, but I want to use an alternate formula here. And what is that formula? That formula is F is equal to ILB. I hope you remember this formula. This formula allows us to calculate the force on a conductor which already has this current I in it. Okay, ILB. Now, if this is the force on the conductor, what will be the power? Power is force into velocity. Power is equal to force into velocity, and it also represents the rate of the work being done. Okay, so the power is equal to force into velocity. It is I L B V. Have you understood this? Power is force into velocity, force is ILB into V. Is that clear? Or no?
हो.
ओजस तुला कळालं, मानसी तुला कळालंय काय? Mansi is not responding. Anyways, so power is the rate at which the work is being done. So it is ILBV. Now recall that in the second chapter, electric potential and capacitance, how have we defined the electric potential? Okay, or EMF now. Potential difference, it is the work done per unit charge. It is the work done per unit charge. Now how can we incorporate how can we incorporate this thing there? Remember, this is the rate at which the work is being done. So this is dW by dt. Okay, this is dW by dt. And if I now talk about W's derivative from this relation, this is okay, this is potential as work done per unit charge. It will be EQ, and here dW by dt is equal to EI. Okay, E into I, because what is dQ by dt? dQ by dt is nothing but the current. And if this dW by dt, which we have got from the second chapter definition as E into I, if we apply that to this dW by dt which we have got here by using the modified version of the Lorentz force, we can say that EI equals I B LV. Cancelling the current, we get E as BLV. So either by using the approach of Faraday lens, we arrive at the same expression, E is equal to BLV, or if we use the Lorentz force and the definition of electric potential, EMF, change in potential, we still arrive at the same result, that is E is equal to BLV. Please try to understand what is this expression telling us. This expression is telling us that if there is a conductor moving with velocity v normal to magnetic field B bar, then there will be an EMF induced at the between the ends of the conductor, which is given by E equal to BLV. And if you want the electric current to flow, then you can join the ends of the conductor by means of some other metallic conductor or some metal, and then the current will flow. And the magnitude of the current will of course depend on the resistance of that particular wire and this wire. This is called as slide wire generator or motional EMF due to slide wire, because the wire slides. Have you understood this? Yes? Okay. Next. Now this quantitative study has been deleted from this year's course, so I will not be revising, although in the theory class I've already taught you that. Okay. But well, I'll just summarize this for you. The mechanical power generated, the expression for the mechanical power generated or supplied, I would say, mechanical power supplied, because you need to move this wire in the magnetic field, so you have to apply some force. Okay. That mechanical power is equal to the heat lost, which the expression for the heat lost, we discussed that in our third chapter, current electricity. Heat loss in a conductor, that is I squared R. This is actually the rate of heat being lost, and both the expressions actually match, which confirms that the energy that we spend, or I would say the rate at which we spend the energy to move this conductor in or out of the magnetic field, that causes the electric current to flow. So mechanical energy gets converted to electrical energy because the current is flowing, and this current will then cause the heating of this conductor, and that heat lost is numerically equal to B squared L squared V squared by R, where R is the quantity resistance and we only consider the resistance of PQ, although there will be some heat lost or due to the other parts of the circuit. But if we ignore that, then the mechanical power that we have supplied here, force into velocity, will be equal to the rate at which the heat is lost in the circuit. Both are equal, conservation of energy is obeyed. Have you understood this? Well, it's not bad to know things, right? It's good to know few additional things, and they're part of your syllabus. Unfortunately, due to COVID, they have been omitted from this year's exam. Correct? All right. And yes, and also, okay, and also we can say that the amount of charge that has flown, equals the change in the magnetic flux equals the change in the magnetic flux divided by resistance of the wire. A small mathematical derivation. We start with Faraday's law. Epsilon is equal to delta phi b by delta t. Because the speed is uniform, we omit the d by dt notation and accept delta by delta t. Induced EMF by Ohm's law. Induced EMF by Ohm's law is IR. But what is current? Current is the rate at which the charge flows. Steady current. So delta q by delta tr is equal to delta phi b by delta t. Delta t gets cancelled. You can send this r there. So delta q is equal to delta phi b upon r. And please note here, r is the resistance of wire PQ. R is the resistance of wire PQ. We are ignoring the resistance of the remaining part of the circuit. We are just considering the resistance of the wire PQ, which is actually sliding in the magnetic field. Alright, so you can also remember this as an additional formula. Delta Q does not represent heat, but delta Q represents the amount of charge that has flown. Amount of charge that has flown during that specific time. It is the ratio of the change in the magnetic flux. It is the ratio of the change in the magnetic flux to the resistance of the sliding wire. Got it? Yeah. Okay, now we move on to the next and very important quantity, which we also use in AC circuits quite a lot, and that quantity is called as inductance. Now this particular quantity belongs to the league of resistance and capacitance, because in the next chapter we have seen that we have an inductor, we have a capacitor, and we have a resistor. We call it an RLC or LRC, LCR series circuit, and we can have many interesting applications using that. So what is inductance? We now make a statement. We know this because of the magnetic field generated by a coil, or we can call it a solenoid. What is it? B is equal to mu naught Ni. You know that. For a solenoid, if you take magnetic field inside a solenoid is equal to mu Ni, where N is the number of turns per unit length, I is the current, and B is the magnetic field. Now, if I change the current, magnetic field will change. If the magnetic field is changing, then the flux associated with the same coil will also change. If the magnetic field changes, magnetic flux changes, and there will be an induced EMF, and that induced EMF will be proportional to the rate at which the flux is changing by Lenz's law, and therefore the rate at which the current is changing. Okay, so we will now write this mathematically, but there are two parts here. Which two parts? Let us for a moment go back to the second figure here. The current, the induced EMF or the induced current in coil C1 can either be due to motion of C2, relative motion of C2 and C1. So the flux associated with every turn of coil C1 in this case is changing, not because current in C1 is changing, but current in C2 is changing. That's first way. When such a thing happens, we use a quantity, okay, which depends on the material and the geometry, and we call it mutual inductance. Whereas if you forget, okay, if you forget this coil, just momentarily I'm deleting it. If you forget this and say that the current in this coil also changes, okay, let the current in this coil change, then that change in current will cause the change in magnetic field, okay, with this magnetic field to change, and because magnetic field is changing, the flux associated with every turn of coil C2 will also change, and that will cause another EMF being induced there, and we call it back EMF. And in such a case, the quantity that we associate with it is called self-inductance. So we will now discuss that in detail. But did you understand the 2 points that I made? The EMF that is induced can either be due to changes in the current in some coil, some other coil, or flux change in some other coil, that is mutual inductance, or this induced EMF or current can also be due to changes in the flux by the same coil, and we call it self-inductance. But in either of these two cases, or both put together, one relationship always remains the same. In fact, that is the starting point. What is that relationship? That relationship is this proportionality relationship. N represents the total number of turns, okay, the total number of turns of coil of our concern. Phi is the magnetic flux associated with each turn, one single turn of that coil, and it is directly proportional to the current. Now this current can either be the current in the same coil, or it can be current in the other coil. If it is current in the same coil, then the constant of proportionality will become what? It will become self-inductance L. If this current is changing in some other coil, and because of that you see an induced EMF and current in our coil, then this current will be I2, or the other one, the current in the second coil, another coil, and in that case the constant of proportionality will be mutual inductance M. We have seen that already in our regular lectures, that mutual inductance is the same. So if it is N1 Phi1 proportional to I2, or N2 Phi2 proportional to I1, the constant of proportionality is always the same, and hence we call it mutual inductance. Okay. Now, phi is the magnetic flux associated with each turn. Magnetic flux associated with each turn, and N is the total number of turns. Can you tell me, what do we call the quantity N phi? सांगता येईल तुम्हाला? Can you tell me the quantity this N phi? What do you call it? We call it flux linkage. What do we call it? We call it flux linkage. Please remember this. Flux linkage is basically the total flux. So we defined phi to be the magnetic flux associated with each turn, and N is the total number of turns, so N phi is the flux linkage, and the constant of proportionality in this case, if it is, okay, let me use subscripts now. Suppose we are concerned with currents in the current changing in the second coil, okay, current changing in the second coil, and how much EMF is induced in the first coil. Suppose we are concerned with that, then we will have the mutual inductance M here, mutual inductance M. And if we have the same coil, then we can say N phi is proportional to I, or let me write it N1 phi1 proportional to I1. N1 phi1 is equal to L into I1. Have you got these two relations? Both these relations stem out of the main fundamental relation, N phi flux linkage is directly proportional to current. Is that clear to all of you? Okay. Now the mutual inductance and the self-inductance, they both are dimensionally same, and you can find the dimension of that inductance if you know the dimensions of current and the dimensions of magnetic flux, because N is a number, it doesn't have any dimensions. So you may remember it, the dimensions of inductance, self and mutual, both. ML2 T negative to A negative 2. And it is interesting to see here that just like capacitance, which depends on the material properties and geometry, just like resistance, which depends on the material property called resistivity and the dimensions geometry, just like resistance and capacitance, inductance of an inductor also depends on the geometry and the intrinsic material properties. Please understand that. In case of a parallel plate capacitor, the geometry of the plates, how far are the plates from each other and what is the area of them and what material you put in. The capacitance is totally decided by that and not by the potential difference that you have applied and not also by the charge that you put on either of the plates. So we say that capacitance depends on geometry and intrinsic material properties, just like that. Self-inductance or mutual inductance. So in general, inductance depends on the geometry of the coils, their relative orientations, and also the intrinsic material properties. Okay, what material you put in there in the coil. We already seen that the magnetic field is enhanced if inside the solenoid we put an iron bar. We saw that in our previous chapter where we defined quantities like magnetization and magnetic intensity. Okay, so please remember this. Resistor depends on resistivity and length area. Capacitor, the capacitance depends on the geometry, area and length, the separation distance and the material that you put in, material property. Just like that, the inductance of an inductor, be it self or mutual, depends on geometry and it also depends on material properties. Okay, specifically the relative permeability, but that comes much later. Have you understood this? Yes? Okay. What is the SI unit of inductance? What is the SI unit of inductance? Henry. SI unit of inductance is Henry. Okay. H could have also meant Ritika, but that's Henry. Okay, that was a bad joke. Okay, now let us talk about a very simple expression for mutual inductance. So what is the situation? This figure is from the book and you can see already that the mutual inductance formula incorporates the geometry and intrinsic material properties there. Intrinsic material properties, there is only one term for that, that is mu r, relative permeability. N1, N2, R1 and L, all of them are geometrical parameters. Okay, fine. So basically we have two solenoids here. The outer solenoid is S2. The outer solenoid is S2 and the inner solenoid is S1. The inner solenoid is S1. And I will not go in detail now, but understand that R1 is the radius of the coil, not the radius of the wire, the radius of the coil or radius of the turn of the first solenoid, inner solenoid, and this is outer solenoid. Capital N, uppercase N represent N2 and N1, they represent the total number of turns. If you divide these by L, then you will get the turns density. We are interested in determining the flux linkage due to current flowing in outer solenoid, okay, in inner solenoid. So how are we going to start? We are going to start by writing down the expression for the magnetic field that will be created inside the bigger solenoid, B2. We know it very well, mu naught N2 I2. Is that clear? We are currently assuming that the vacuum is present, so I'm not including the term mu r there, but okay, we can input it anytime. We can incorporate it in it. So have you understood this expression? B2 is equal to mu naught N2 I2. Yes or no? हे कळालं आहे तुम्हाला? हा आपला आधीचा फॉर्म्युला आहे. Exactly. Okay. Okay. Now let us consider the flux associated with one turn of inner solenoid. Well, we can assume that this flux will be B2A1. This flux will be B2A1. Why is that? Magnetic field is due to outer solenoid. Turn of S1, so area of that. We can say it is B2, so just write phi here. Mu naught N2 I2, then A1, so I can write it as pi R1 squared. Area, assuming the circular turns, this is the magnetic flux. Now, what is the flux linkage? Flux linkage requires us to multiply, or rather to add the flux associated with every turn. So how many turns are there now? N phi will now be equal to, now how many turns are there? Turns density is N2, so N2, wait, we need to consider N1, right? Okay, so flux linkage will be N1 phi, so that will be N1 into L phi. So that is what? Mu naught N1 N2 I2 pi R1 squared L. We are almost there now. Please note what we did here. We said if this is flux associated with one turn, let us now calculate the flux linkage, the net flux associated with all the turns. So for that we have to multiply phi by the total number of turns that exist for solenoid S1. So that will be the turns density small n1 into the length of the solenoid L. So on this side, in this term, there will be two more terms appearing, n1 and L. Okay, n1 is here and L is here. But then if we go back to our fundamental relationship, what is that? Flux linkage is directly proportional to current. Flux linkage is directly proportional to current, which gives me, see, I can happily now remove what? I can happily remove I2. After all, what do I want? What do I want to utilize, make use of? I want to make use of the proportionality relationship between N1 phi and I2. And then if you replace that proportionality sign by an equality sign, the constant of proportionality that pops up there is our mutual inductance. So mutual inductance will be M, can call it M12 or M21, doesn't matter. That is Mi2. What remains is our mutual inductance. Mu naught N1 N2 pi R1 squared L. Mu naught N1 N2 pi R1 squared L. If instead of vacuum, if there is some other material, then you have to multiply it by the relative permeability of that. That's mu. Have you understood the derivation of mutual inductance? Quite simple, and I have emphasized it because this relationship is a new relationship, as in we have not seen this before and also not utilized this before. N phi directly proportional to I, and it is useful in two different contexts: mutual inductance as well as self inductance. Any doubt here? If yes, please ask me. No doubt. Okay. No doubt. Yes. Okay. So this is what I was talking about. For resistance, the relationship is V equal to IR, where capital R is the resistance of a resistor, depends on geometry and material properties, that is resistivity. For capacitance, the voltage is Q by C, right? Voltage is Q by C, and Q is the charge, C is the capacitance, again a constant for a given capacitor, depends on the material properties and geometry. So what about inductance? Can we calculate the EMF induced there? Yes, of course we can calculate it. So how to do that? To do that, we will start with N1 phi1 equal to m I2. Now I will apply Lenz's law. By Lenz's law, induced EMF is negative of the derivative of the flux linkage. Okay, N1 phi1, yeah, N1 phi1. N1 is, okay, but what is N1 phi1? It is m into I2, so it is negative m di2 by dt. This is how we write the induced EMF as, or in terms of the rate of change of current in some other circuit. E is equal to negative m di2 by dt. So please note, for resistor it is V equal to IR. For resistor it is V equal to IR. For capacitor it is V equal to Q by C, and for inductor it is E equal to negative m or L di by dt. If you remember, we have used this expression. Where have we used it? We have used this expression in IISER series circuit in the next chapter. Okay. Alright, when you apply the Kirchhoff's voltage law there, this is useful in KVL, in AC circuits. But there we use self-inductance, which we will revise now, but the form remains the same. Okay, let's now revise self-inductance and back EMF of the coil. Okay, we call it back EMF because again we know the induced EMF is going to oppose the change that caused it. So let us consider a circuit here. Shown here is a battery, but let's assume that the current is building up. Initially it was 0 and now it is increasing. Okay, same relationship, N phi b is proportional to I, and we can remove it and get or write L here. This L is called as the self-inductance. Same SI on it, same dimension as that of mutual inductance. I'm not going to derive the expression now. You can derive it in a similar way. All you have to do is you have to start with this mu naught Ni. Okay, and in usual notations you can arrive at this. Here capital A represents the area of the turn. Area of one turn. It's not the cross-sectional area of the wire, mind you. It is this area. Let me highlight it in red color. It is this area. Okay, this area of one turn. And then you multiply it by A, differentiate it, then you will get flux multiplied by N, and then we equate this. This mu naught and N will appear one more time because of this, and N will also appear. Okay, so this is self-inductance, and therefore the induced EMF, we call it back EMF of the coil. Do you think that you can handle this part on your own? If not, please refer to our notes, our regular lecture notes, so you'll understand what I'm explaining. But essentially the, sorry, समझ लो ना? So essentially you have to follow the same approach but without subscripts, because there is only one coil here, that is self-inductance. Then back EMF, let me write it. Back EMF is negative L di by dt. This is what we have used or we use. This is what we have used or we use in AC circuits. Okay, and this also allows us, this is the starting point of our conclusion, that in a purely inductive circuit, V or E leads I by pi. Okay, we can derive from this. Anyway, self-inductance. Now, the energy required to build a current I in this circuit, we know the expression here. How much energy do we need? That energy, we call it magnetic potential energy. It is half Li square. I am not going to derive this right now, but note the resemblance between this and half CV squared. This is the electrical potential energy stored in the capacitor when it is charged. This is the magnetic potential energy of an inductor. Okay, now why is this energy required? This energy is required because the very characteristic or very phenomenon of the electromagnetic induction is to oppose the change that is creating it. So if you want to force the current to pass through it, if you want to increase the current that is flowing through it, you have to supply energy. This energy we are assuming is not being spent in overcoming resistance. So this is for a pure inductor. This is for a pure inductor. So there is no energy dissipation here. The energy is still stored there in the magnetic field. Just like here we say that the energy is stored in the electric field between the plates where you place the dielectric, or if not then vacuum. So this is pure inductor. And remember, when we are discussing LC oscillations later in AC circuits, we made a point there that after some time the oscillations decay because of two reasons, and one of the reasons was you cannot have a pure inductor. The inductor will have some non-zero resistance, and that will cause the vibrations to, or oscillations, not vibrations, oscillations, LC oscillations to decay. But if we assume it to be an ideal inductor and an ideal capacitor, then there will be an interplay between this energy stored here and the energy stored in the capacitor. We have seen that, or rather we will see next in the next chapter when we revise that. So what is the energy required to build the current? Half Li squared. L is the inductance, self-inductance. It is also analogous to mass, and current is analogous to speed. So this potential energy, magnetic potential energy, resembles the kinetic energy of a moving body, but these are only crude analogies. Don't think that this actually represents kinetic energy. No, it's not. Okay, it doesn't. That's energy required to build the current. Now, if we put the self and the mutual inductances together, then the EMF that is induced in our coil, let us say epsilon 1, okay, it will be algebraic addition of two things. Another coil, so it will be negative M12 di2 by dt plus negative L di1 by dt. Okay, if there is no other coil in its vicinity, this term will go. Okay, and if no current is flowing through your coil, then this term will be there. But generally di1 by dt will always be there. Okay, fine. Last part of the chapter, generator and alternating current. So in this part, let me return to the beginning where we talked about magnetic flux. What can change magnetic flux? Either field or area or theta. So here theta is changing, the angle between B bar and A bar, and that is the case that we will discuss. It's very simple. It is very simple. We start by writing down the magnetic flux expression B A cos theta. Let us assume that this coil or armature is being rotated with uniform angular velocity omega. Uniform angular velocity omega in radian per second. And then if I apply Lenz's law here, E is negative of d phi b by dt, B is not changing, A is not changing, derivative of cos theta is negative sin theta d theta by dt, negative, negative, positive. So it will be BA sin theta d theta by dt, but d theta by dt is angular speed omega. It is constant in this case, or rather in general it is constant. And the rotations that our coil completes in 1 second, in India that frequency f is 50 Hertz, and therefore omega, the angular frequency, is 100 pi radian per second. And this gives rise to alternating current. So the current not only keeps on changing in magnitude, but it also keeps on changing in direction. And how many times does it happen in 1 second in India? 50 times. 50 times. And later on in the next chapters we'll see that's why we need to bring in the quantities like RMS voltage, RMS current, so that we can compare it with an equivalent DC circuit. So this completes the revision of electromagnetic induction. If you still have any doubts, you can ask me. Otherwise, we will, or that should be the end of the start.